a very practical question. Can a world model learn straight from pixels without a bag of training tricks quietly holding it together? LeWorldModel says yes. It uses a simple JEPA setup. Encode the current frame, predict the next embedding from the action, and keep the latent space shaped like a Gaussian so everything does not collapse into one boring point. The neat part is what that buys you. A 15 million parameter model trained on one GPU can plan much faster than foundation model-based alternatives while staying competitive on control tasks. Its latent space also carries physical structure, enough to decode position, support planning, and get more surprised by teleporting objects than by mere color swaps.
Joint embedding predictive architectures, or JEPAs, have become a go-to for building world models, but let's be honest, they've historically been a bit of a headache to work with. You usually need complex setups, like pre-trained encoders or moving averages, just to keep the training from falling apart. This paper introduces a much cleaner, simpler way to do it. The model starts by taking raw pixel inputs and mapping them into a compact latent space using an encoder. From there, a predictor tries to guess the next state based on the current state and the action taken. The training itself relies on just two things: a standard prediction loss and a regularization term called sigreg. Think of sigreg as a way to keep the latent space healthy. Instead of letting the model collapse into a single point, it projects the latent embeddings onto random directions and forces them to follow a Gaussian distribution. This ensures the model learns diverse, meaningful features. By doing this, the authors cut down the number of hyperparameters significantly, making the whole system much easier to train end-to-end on a single GPU while still performing well on complex control tasks. To see why this is such a big deal, we need to look at the current landscape of world models. If you look at Figure 2, you'll see a breakdown of the status quo. You've got older methods that are either incredibly complex, requiring endless hyperparameter tuning, or they rely on crutches like pre-trained encoders or specific task rewards just to stay stable. The core issue with many of these models is collapse, where the model just stops learning anything useful and maps every input to the same output. To fix this, researchers usually throw in complicated heuristic-based loss functions. This paper argues for a much cleaner path. By being end-to-end, task-agnostic, and reconstruction-free, the proposed model avoids all that baggage. It doesn't need to reconstruct every pixel or know the specific task reward beforehand. Instead, it focuses on learning a stable, compact representation of the world using just one hyperparameter. It's a huge relief to be able to train this on a single GPU without the usual headache of balancing a dozen different loss terms. Let's look at the performance data in Figure 3, which really drives home why this approach is so efficient. The first chart compares planning time. Because the proposed model uses about 200 times fewer tokens than the foundation model-based baseline, it can plan in under a second, whereas the baseline takes nearly 50 seconds. That is a massive jump in speed. The center and right charts show success rates on two different tasks, push-t and OGB-cube, while keeping the computational budget fixed. In both cases, the proposed model significantly outperforms the baseline. For instance, on the push-t task, it hits a 90% success rate compared to just 13% for the baseline. This leads us into the related work section, which frames these results within the broader history of world models. It distinguishes between generative models that try to simulate pixels, which often rely on reward signals, and the JEPA approach. JEPA is different because it works in a compact, low-dimensional latent space. The authors note that while previous JEPA methods often used crutches like exponential moving averages or pre-trained encoders to prevent the model from collapsing, those methods lack a solid theoretical foundation. This sets the stage for why their new, simpler approach is a necessary evolution. Now that we've covered the background, let's look at how the model actually plans. Figure 4 illustrates the latent planning process. It's a clever way to use the world model we've trained. You start with an initial state and a target goal, both converted into compact latent representations. The predictor then simulates a sequence of future states by applying a series of actions. Think of this as the model imagining what will happen if it takes certain steps. We then calculate a cost based on how far the final imagined state is from our goal. A solver then tweaks those actions to minimize that cost, essentially refining the plan until it finds a sequence that successfully reaches the goals. The rest of the page shifts to the formal methodology. The authors emphasize that they are working in a fully offline, reward-free setting. They aren't trying to solve one specific task. Instead, they are learning a general-purpose model of how the environment works. By training on unannotated trajectories, they ensure the model captures the fundamental dynamics of the world, which can then be adapted to almost any task later on. Getting into the how-to of the architecture, the model uses two main parts: an encoder, which is a tiny vision transformer, and a predictor, which is a transformer that takes in a history of states and actions to guess what happens next. To train this, they use a two-part objective. First, there is a prediction loss, which is just the squared difference between the model's guess and the actual next state. But as we've discussed, relying only on this leads to collapse, where the model gets lazy and outputs the same thing every time. To fix this, they add the sig-reg regularization term. Since checking if a high-dimensional space is normal is mathematically hard, they use a clever trick. They project the latent embeddings onto many random one-dimensional directions. By forcing these projections to look like a standard bell curve, they ensure the entire latent space stays diverse and well-structured. The final training goal is simply the sum of the prediction error and this regularization term, balanced by a single weight. It's a remarkably clean and elegant way to keep the model from collapsing. This page gives us the recipe for the model. Algorithm 1 is super clean. It shows that the entire training process boils down to just a few lines of code. You pass in your observations and actions, run them through the encoder and predictor, calculate the prediction error, add the regularization term, and you're done. It's refreshing to see such a streamlined approach compared to the usual complex training loops. Next, the authors dive into latent planning. Once the model is trained, they use it to solve tasks by searching for the best sequence of actions. They define a cost function that measures the distance between where the model thinks it will end up and where it actually wants to be. To solve this, they use the cross-entropy method, which is a standard way to iteratively refine a plan. They essentially sample a bunch of potential action sequences, see which ones get them closest to the goal, and then update their strategy based on the best performers. It's a classic optimization loop that turns the world model into a functional decision maker. This page sets the stage for how the model is actually tested. Figure 5 shows the 4 environments used: push-T, OGB bench cube, 2-room, and reacher. These cover a good mix of 2D and 3D tasks, ranging from simple navigation to more complex robotic manipulations. To prove the model's worth, the authors compare it against several strong baselines, including other state-of-the-art JEPA-based methods and offline reinforcement learning algorithms. They are careful to ensure a fair fight. For example, they strip away extra information like proprioceptive inputs from the baselines so that everyone is working from the same raw pixel data. The results are quite compelling. The model shows an 18% higher success rate on the challenging push-T task compared to the closest baseline. Even more impressive is that it outperforms a baseline that had access to extra physical data, which really highlights how well the model captures the underlying physics of the environment. Plus, the planning speed is nearly 50 times faster than the competition, which is a massive win for anyone trying to run these models in real time. This page dives into the results and the why behind the model's stability. Figure 6 shows that the model is a strong performer across most tasks. Interestingly, in the very simple 2-room environment, the model performs slightly worse than the baselines. The authors explain this as a potential limitation. The regularization term is designed to force the latent space to look like a standard bell curve, which might be overkill for a task that is inherently very simple and low-dimensional. Next, the authors discuss why the training is so stable. They performed ablations, which is basically testing how sensitive the model is to different settings. They found that the model is robust to most internal parameters, meaning you don't have to spend forever tuning it. You really only need to worry about one main hyperparameter. They also compared their training curves to the baseline. While the baseline's training loss is noisy and jumps around, their model shows a smooth, steady decline. This confirms that by stripping the training objective down to just 2 well-behaved terms, they've successfully removed the headache of balancing competing gradients. This page is all about proving that the model actually understands the physical world, not just pixels. First, they use probing, which is a common technique where you train a simple model to extract specific information, like the location of an object from the latent space. As you can see in Table 1, the model does a great job of encoding these physical properties, often beating the baseline models. Next, they look at decoding, where they train a decoder to reconstruct the original image from just the latent representation. Even though the model was never trained to reconstruct images, the decoder can still recover the scene, which proves that the latent space is holding on to all the important information. Finally, they touch on temporal path straightening. This is a cool concept from neuroscience that suggests that as a model learns, its internal representation of a trajectory becomes more straight or predictable. They found that their model naturally develops this property without any explicit training to do so, which is a strong sign that it's learning the underlying physics of the environment in a very natural, efficient way. We've reached the final page, where the authors wrap up with a visual sanity check. Figure 7 shows the model's imagination in action. By taking a few initial frames as context, the model predicts what will happen next in the environment. When you compare these imagined frames to the real ones, you can see that the model does a great job of capturing the overall movement and structure of the scene. It's not perfect. It might miss tiny details like the precise angle of a robotic arm, but it's clearly learned the fundamental physics of the world. In the conclusion, the authors summarize the core value of their work. They've created a stable, end-to-end way to learn world models that doesn't rely on the usual complex tricks. By simply encouraging the latent space to follow a standard Gaussian distribution, they've made training much more reliable. They wrap up by acknowledging that while this is a big step forward, there's still work to be done, particularly in extending these models to handle much longer planning horizons. It's a solid, principled foundation for future research. We're wrapping up with some really cool visualizations. Figure 8 shows how the model's understanding of the world improves as it trains. Even though it isn't explicitly told to reconstruct images, you can see the decoded output getting sharper and more accurate over time. It's a great way to see the model learning to capture the essential features of the environment. Figure 9 is even more insightful. It compares the actual physical grid of positions in the push-T task to how those positions are mapped in the model's latent space. You can see that the model preserves the spatial relationships. The grid structure is still there, just slightly warped. This is a huge deal, because it means the model isn't just memorizing pixels, it's actually learning the geometry of the world. Finally, the authors discuss the remaining challenges. They note that while the model is great, it still needs a good amount of offline data to work well. They also point out that relying on action labels can be expensive, and they suggest that future work could focus on learning these action representations automatically, which would make the whole system even more flexible and easier to deploy. Thanks for joining us today. Happy exploring together!